All right, now we've gone through the definitions. What are the attributes of an error? What is proportional, integral, and derivative? And we threw in on-off control. Now we're going to talk about the interactions. P by itself results in an offset. I by itself results in an oscillation. D by itself is never used. But what's interesting is when you add them together, it's like you get 1 plus 1 plus 1 equals 1,000. The sum of the parts is greater than individual contributors. That's what I guess I still find that kind of fascinating. Is you take these by themselves that aren't really that good and you put them together and you get a workhorse that represents 90 to 95% of all automation in industrial systems today. This is just a quick review to show that we have the attributes of a set point, and then the measure value moves away from it for whatever reason, a disturbance, a load change, something happened. And there's three things: magnitude of error, which represents the present error, the duration of the error, which is sort of the past error, and then the rate of change, which is where's this thing going. And those directly align with proportional, integral, and derivative. However, we just went through a whole session on process dynamics. How do I calculate a process gain? How do I calculate a time constant? How do I calculate a dead time? How in the world does dynamics of the process translate into this? Well, we're not quite ready to answer that, but we're getting close. Now what we're going to go through is understand the interactions. We're going to start with proportional integral by themselves, and then we'll add derivative later, because derivative really isn't used that often. So let's understand the P and the I. Things that you have, they talk about integral time, integral gain, reset time, repeats per minute, minutes per repeat. What in the world's all that stuff? Hopefully this section will answer that. That's what I was saying. Proportional by itself isn't used that much. Integral by itself can result in it's just not fast enough to catch up with errors. And derivative is never used by itself, or you would just tear up your actuator. So again, by themselves, they're not very powerful, but when you put them together, they're very powerful. And this is why. Everybody likes the proportional kick that you get with the proportional action, but it leaves an offset. Everybody likes the fact that the integral will force the error to 0, but it's too slow to act. Someone says, well, what if we put them together? P plus I. Well, guess what? You get the proportional kick and the integral kick. This relationship, it represents almost 100% of industrial controllers use a PI control. Today everybody's talking about modern control theory and MPC and APC and dynamic matrix control theory. Those are all wonderful disciplines, but at the foundation is this stuff. And if the PID algorithms don't work, none of the fancy math or the fancy algorithms have a chance. So the core backbone of automation is the PID algorithm. Now, KC controller gain, that's where now it gets a little fun, is controller gain, a proportional band. Sometimes they'll call it G, sometimes they'll call it K, sometimes K sub C. If you look at the ISA naming conventions, K represents gain, the subscript C represents controller. So a controller gain, how does that relate to the process? We've seen that it is inversely related to the process gain. The integral time, we're trying to figure out, I implied that it was related to the process. You can kind of make sense out of that based upon the mass or the inertia in the process. The integral time has to be proportional to that. That's what we're going to talk about here a little bit. Now, suppose, and I've done this when I would get a controller and I just didn't know what it was. I would hook it up to a test bench in an E&I shop, and that way I had the controller, I'd put the error to it, or the 4 to 20 milliamps, and I would cause a step error, or a disturbance, and then I would watch the output. And based on how the output moves, based on what we just talked about with proportional integral derivative, I could tell the form of the PID algorithm. I could tell if it was minutes per repeat. I could tell all that. A lot of times, that's a last resort. Usually you can go to the customer's documentation on that particular controller, and you'll find an algorithm or a type. And that's what I've got at the end of this, the end of this series, is different types of controllers. So I'll show you that here a little bit. So here's the experiment. You walk up to a bench-mounted controller. Again, there's no process. You can see that when the set point and the measured value are right on top of each other, there is no change in the output. Now, all of a sudden, we change the set point. So by changing the set point, we get an initial kick, boom, and that's from the proportional. Well then, because the error hasn't changed, proportional, so I'm done. But then I says, well, shoot, I got to do something. So this continues to grow. So here's what you got. That's what I was saying, as it's important. I like to do this if I can in a bench setting or something, is to just sort of see if I know how much this moved as a relationship to this. I know the type of proportional gain. Is it in percent? Is it in customer units? Is it proportional band? And I can look at the slope here as a function of this area, and I can calculate if it's in minutes or seconds or whatever. So we're going to talk about that, but this is an actual real picture that you can get. Now, when you hear the term reset time, that was confusing for a long time. A lot of people said reset time. Oh, reset, that means I do nothing and then I reset. That's the wrong interpretation of reset time. Or repeat time is, well, what in the world am I repeating? Well, when P and I are working together, your proportional kick happens when you have a step error. Then integral takes over. And someone said, boy, it sure would be nice if the integral time was related to that original proportional kick. So they said, okay, here's my original proportional kick. How much time does it take for the integral to add up to the original proportional kick? That's called the repeat time or the reset time. You're not resetting anything. It's just a measure of time until the integral has added up to the original proportional kick. That's where it gets interesting. Depending on what vendor you're working with, they'll either give you an integral time in seconds, or they'll give you an integral time in minutes, or they'll give you a gain, which is the slope. And it can be in repeats per minute or repeats per second. So there's 4 different things that could represent this picture. Usually you just have to go to the documentation for the vendor. Sometimes you can tell by the units on the integral gain, and sometimes you just have to drop back to a bench mount, or with today's controllers you can set up a generic controller. I've done that. Set up a little display and you have a dummy controller and you just change the value and watch the output. If you're really unsure, don't start on a real process. You really need to know the units and know what you're working with. Now let's talk about this. When you put these together, think of the integral is like a, am I there yet? Am I there yet? It's like the little kid in the back seat. Are we there yet, Dad? And just give me time. We have to travel here. That's kind of what integral is. Now, if the answer is no, meaning the process has not yet reached the set point, then the integral control will continue making changes. It integrates until the answer is yes. If the process is slow moving, meaning it's a large time constant, if the question is asked too often, what do you expect to happen? Other than if you're a parent, you'll get very annoyed. That's what, in a process, if the integral is asking too fast, based on how fast the process can respond, you break your actuator. And so that's what we need to realize, is that the integral time and the process time constant, they're related. They're actually proportional, directly proportional. So this is what can happen when the PI combination is set such that the integral is repeating the proportional too fast. I once told someone this is ringing, and so I don't hear anything. Yeah, this is what it looks like when a process rings. If you could hit a bell and watch the sound waves, it would look very similar to this. That's what it looks like. So I call that ringing, and I can still remember. Said, "Well, I don't hear anything." And I go, "No, it's not. Sorry, it's oscillating. It's just oscillating in an underdamped manner." But this isn't good. So this would say that your integral, you're resetting too fast, or your proportional gain is too high. Remember, they're related, and I'll talk about that. And that's what tuning is how do I adjust this? This is what happens if your reset time is too slow. So the process is like, okay, when are you going to make a change again? So it just very, very slow. So in terms of the question is if the integral time is big as compared to the dynamics, is that a stabilizing or destabilizing effect? So is this stable or is this stable? If you're going to make a mistake on integral, you want to go a little big on the time, so that you build in a stabilization. You want to avoid an oscillation almost at all costs. I would say at all costs. All right, now, if you look at this, what I'm showing you here is your original kick, and you can see I have a very short reset time. So what you would expect is an output that just takes off. Only way that can work is if you have a process that's really snappy, small time constant. Then as your time gets bigger, you can see that your slope changes. So by increasing the integral time, your reset time, it takes longer. That has to happen when you have a slow process. And that's what we did. That's why we spent all that time in the previous videos talking about process dynamics. If you don't know the dynamics of your process, you're going to have a hard time tuning. You'll just be guessing. Once you know the dynamics of your process, then tuning just becomes almost a calibration step. But we're going to talk about that. Okay, so here we were talking about the relationships between proportional and integral. If we have a constant proportional with different integrals, that makes sense. You know, if you bumped it 3 times, proportional is the same kick, but the integral changes. Over here, I have the same integral but different proportional. Notice this is showing 3 subsequent bump tests all overlaid, and we're talking about the output. So what I see here is in the first step it's proportional, then that's proportional, and so the way you look at it is if you could draw a line, how long does it take for this integral time to add up to this? Well, that's how long it takes. So the integral time, the effective integral time is the same. That's called the standard form of the PID algorithm, and we'll look at that in more detail. But this is showing how the proportional and integral work together. When you do that, the PI together can automatically eliminate steady state offset changes. That's really the benefit. Proportional by itself results in an offset. Integral by itself takes too long, but together you can nail the error and keep your error 0 or close to 0. Because of that, the P and the I algorithm are the most commonly used 2 parameters in the industry today. Matter of fact, a lot of times I'll look at derivative, and if they have values in derivative, I really question why they have so many. It's usually a red flag. So when a lot of times I'll dump all the tuning parameters out of a system and I'll look and see how many derivative. And especially if the derivative is a big number, because of the noise in today's systems, what's happening is the derivative number gets smaller and smaller and smaller until its effectiveness drops. So those are indicators of the tuning methodologies that these places use. So derivative, most of the time you're better off to set it to 0 because the PI is so powerful. You have 2 parameters. You don't just have 1, but 2 parameters, the P and the I. The adjustment of those is what's called tuning, and that's what we're going to cover when we get into control tuning. The PI doesn't concern itself with rate of change. Derivative, when added to the mix, does act as a lead, and I've used it when there's like a known limit cycle. I can adjust the output. Think of it like if you're timing a car, you can change the timing. That's kind of how derivative works. Most of the time that's an advanced use of the PID algorithm, and most of the times it's not needed. So the P and the I together work as a powerhouse, so you really get 1 + 1 equals a huge benefit to the automation world. So if you understand the concepts that we've covered so far, then going into tuning will not be such a big deal. And I've used this to troubleshoot. If you walk up and you can look at the dynamics of the process and you can see what the output's doing, you can say, ooh, that's not right. Or if you don't know what the controller is and you can make a generic controller or you can put up a bench test, you can tell how the tuning interact. That covers PI and D interactions. What we're going to cover next is what's called the forms, or there's 3 different forms of the PID algorithm that you really need to know about. Otherwise, you're going to get yourself in trouble when you get out there to the real world.